Okay, so we just talked about welfare economics, a review of welfare economics with an externality. Now let's do a quick little review of kind of environmental economics. If you've taken environmental econ, you've probably seen this graph. So this is going to be talking about what's the most efficient way to achieve the optimal level of emissions, and how do we determine what the optimal level of emissions are. So the graph you're looking at now has emissions on the x-axis, E, has dollars on the y-axis. We have a marginal damage function sloping upwards. This is the marginal damages of emissions. So every unit of, the way I draw it here, as opposed to the welfare graph, the marginal damage of emissions is actually increasing with every unit of emissions. So that's just maybe more realistic. So the first unit of emissions has very small damages, but the last unit of emissions has really high damages. So some people, if we're thinking about climate change, we might draw this as an exponential function. So going further and further out on the x-axis should actually cause damages to increase exponentially. Maybe we hit some tipping points, for example, in climate change, and the damages are going to be, we can't reverse our course at some point. The downward sloping curve here is the marginal abatement cost curve. So this is the abatement, abatement being the reduction of emissions. So abatement is going this direction, reduction of emissions is going that direction, abatement, and pollution is going this direction. So here at 0, we have 0 emissions, so 0 pollutions. We've abated all of the emissions. If we have no regulation, then we are at EU, where the marginal abatement cost curve intersects the E-axis. So that's the unregulated level of emissions with 0 abatement. So that's how much we would emit if we did not abate any of our emissions. So pollution would be all the way up to EU. So with this graph, we can actually figure out the efficient level of emissions. Where's the efficient level of emissions? Well, it's going to be the place where the marginal damages equal to marginal abatement costs. We like to set marginal things equal to each other in econ, so that's going to be right here, E star. This actually gives us an efficient price of emissions as well, P star. So P star would be the price of emissions. What do I mean by a price of emissions? Well, price of emissions could be the optimal tax on the emissions. This could be the Pigouvian tax, if you've ever heard that term. In the previous analysis, the welfare calculations, if Q star was the optimal level of emissions, or if Q star was the optimal level of consumption leading to the optimal level of emissions, then the externality here, the tax imposed, would be a Pigouvian tax, the tax that's getting us to the optimal level of emissions. That's P star in this graph. So that's how these two graphs connect. P star is the tax, the price of the tax, the optimal tax. Okay, so how can we look at this graph? What is this graph telling us? So we have some areas here, A, B, now let me give you C. So A is equal to total damages, TD, at E star. So it's going to be the area under the marginal damage function is the total damages of the emissions. So damages being the damages of the externality or the pollution or whatever it is that we're dealing with. The total damages at E star, so up to the quantity consumed. B, so this is assuming we're consuming up to E star. B is going to be total abatement costs at E star. What are the abatement costs? So it's not free to reduce emissions. So remember when we went to Rawhide, they talked about installing scrubbers, pollution scrubbers, the things that take mercury and SO2 out of their emissions. That costs them money. And that's abatement when they're removing those emissions or those pollutants from their emissions. That costs them money, and so that's going to be their abatement costs. They're abating their emissions, that cost them money, so the total abatement cost is going to be B at E star, the optimal level of emissions. Suppose we are in an unregulated market, so emissions are up to EU, then ABC equals total damages at EU, or if we're in an unregulated market, a market without a policy, then total damages are A, B, and C. And there are no abatement costs. So this could be the, for example, the market for CO2. We don't have policies currently that reduce our carbon emissions in general in the United States. There are some states that have policies that reduce carbon emissions, like California, some up in the Northeast, but in general we don't have a national policy to reduce carbon emissions. And so we produce carbon emissions all the way up to EU, the unregulated level. So we have total damages of A, B, and C, the area underneath the marginal damage function, all the way up to EU. And there are no marginal abatement costs, or no abatement costs, because we aren't abating the emissions. So the question, well, first, let's move to, can we identify some deadweight loss in this graph? So let me erase this. Okay, we still have E star. Now we're going to have a couple of other levels of emissions. So here's E star. This is going to be E double prime. This is going to be E prime. Now let's put some labels on these areas: A, B, C, D, E, and F. All right, suppose we set E at E star. We know that total abatement costs, let me get rid of these. If we set E, suppose we set E at E star, set emissions at E star. Suppose E, that's too many lines, suppose E is equal to E star. Emissions are equal to the efficient amount. Total abatement costs, well, total abatement costs equal C and F. Area C and F. Area under the marginal abatement cost curve between E star and EU. Total damages are equal to E and B. Now let's set, suppose E is equal to E prime. E prime. Total abatement costs are equal to A, B, C, and F. It's the area under the marginal abatement cost curve all the way up to E prime. So going backwards from EU up to E prime, that's our abatement cost, the cost of reducing the emissions from EU to E prime. Total damages in this case equal to E. So the deadweight loss of reducing our emissions too much, so we've gone, the efficient level of emissions is E star, we've gone from EU all the way to E prime, so we've reduced our emissions more than we actually really need to, so the deadweight loss is going to be A. Okay, suppose, now one more, suppose E equals E double prime. Total abatement cost in this setting, so we've gone from EU to E double prime. The total abatement costs are only the area F, the marginal abatement costs underneath the marginal abatement cost curve between EU and E double prime. Total damages are going to be E, B, C, and D, and then deadweight loss is going to be D. Okay, so we have, given the way I've drawn this graph, the deadweight loss in both settings is, the deadweight loss is equal, regardless of whether or not we go too far in reducing our emissions. We go from E, we go past E star all the way up to E prime, or we don't go far enough, we only go to E double prime. But if you can imagine, if we increase the slope of the marginal damage function, maybe we give it some curvature so it gets steeper the further out we go on the E axis, then the deadweight loss is going to increase if we don't reduce our emissions enough. So the area D is going to increase if there's some curvature in our marginal damage function. It starts to increase in its slope. So this graph indicates that the efficient level of emissions is not zero. We don't really want to go all the way to zero emissions, because we receive some benefits from emitting. We like to have electricity in our homes. We like to turn lights on. We like to drive our cars. We like to fly in airplanes. We get benefits from doing the things that we do that impose externalities. What we want to do, though, is in an unregulated market, we're emitting all the way up to EU, and we have some deadweight loss. We're emitting more than we want to, or more than what is economically efficient to emit. So we want to reduce our emissions down to E star, and we do that by imposing some sort of policy to achieve a lower level of emissions. And what we see here in this graph is that if we don't reduce our emissions enough, then we still have some deadweight loss. If we reduce our emissions too much, then we also have some deadweight loss. So one thing you could ask yourself is it better to reduce our emissions too much or not enough? Which going too far or not going far enough, which do you think is going to impose the larger deadweight loss? It depends on the shape of the marginal damage function and the marginal abatement cost curve. Probably it's better to err on the side of reducing our emissions too much, because the marginal damage functions are going to be probably more exponential. They're going to be increasing faster than the marginal abatement cost curves are going to be increasing. Marginal damage functions go from left to right. Marginal abatement costs go from right to left. So in reality, it's difficult to actually hit E star. It's difficult to know what E star actually is. But that's where we're going in this class. We are going to try to figure out the optimal level of emissions, or at least the optimal tax on emissions, the tax on CO2. That's the next portion of this class. So questions we want to ask for policies. What policies are the most cost effective? What policies are the most politically viable? So cost effective being cost us the least overall. What policies are the most politically viable? Which ones can we actually implement? And what policies are economically efficient? What does it mean to be economically efficient? Well, some policies are only going to get us to E double prime, and some are going to get us too far, E prime. The efficiency is going to be the policy that gets us to E star, the optimal level of emissions. So the first discussion question for this week is going to be what is going to be the most economically efficient method for reducing emissions and internalizing the externality? Or what policy is the most efficient policy for reducing emissions and internalizing an externality such as CO2 emissions?